Welcome back. In this section, we'll be talking about trigonometric identities. Just first off to clarify, when we talk about an identity, we're talking about some sort of an equation which is always a true statement, no matter what the value of the variable is. So something like this equation that I have here, x minus 1 equals 2x minus 2 over 2. That's an identity because no matter what value you put in for x, what you'll have on the left side of the equation will always be equal to whatever you have on the right side of the equation. So you would call this equation an identity. If you have a statement that's not always true, you could call it a conditional statement. Something like x minus 1 equals 5. That's a conditional statement. It's true sometimes, but it's not true all the time, which means it's not an identity. The only value of x here that makes the left side and the right side equal to each other would be the value of 6. But for any other value of x, the left side and the right side are not equal to each other. So that's why that's not an identity. What we're going to be looking at in this section is old identities that we've already established and using those to establish new identities. The identities that we've seen in the past, we know from the even and odd properties of our trig functions, sine, cosine, tangent, and all the rest. They all have either even or odd symmetry. That cosine and secant, those are the two even functions. So cosine of a negative angle equals cosine of the equivalent positive angle. And same thing for secant. The other four trig functions are odd. So you will have things like sine of negative theta equals negative of sine of theta. So that's something that's true no matter what angle we're talking about. For valid values of theta, for angles where secant and all the rest are defined, secant is the reciprocal of cosine, and cosecant is the reciprocal of sine, and tangent is the reciprocal of cotangent. So we have these reciprocal identities. We also have the Pythagorean identities. Those were also always true. Again, no matter what the angle is, if it's an angle where these functions are defined, well, then the left side and the right side will be always equal for these equations. Now, we had originally came up with the Pythagorean identities using a right triangle trig argument. But now we're just going to simplify our life here by doing the same sort of thing, proving our Pythagorean identities, but this time not starting with right triangle trigonometry, starting with the unit circle. So again, reminder that if we're talking about an angle theta, and we're thinking about that angle inside the unit circle, you'll have some point x and y, and the value for r here, if you're in a unit circle, is 1. You know that in a unit circle, x squared plus y squared is equal to 1. And that's, of course, because that's the equation of our unit circle. That's the whole point of why we're using the unit circle, because we know that that gives us a value of r being 1. But we also know that in the unit circle, that x would be the value for cosine of theta. Remember that we had defined in the unit circle that cosine of theta was the x value, so x squared is cosine squared, and the y value is sine theta, so y squared is sine squared theta. And so the reason for this, of course, is because sine theta is y and cosine theta is x in the unit circle. So we've actually established that very first Pythagorean identity, and then the other two identities we can establish in the same way that we did before. Taking that first identity, and if I were to divide everybody by sine squared, if you were to simplify that, cosine over sine is cotangent, so cosine squared over sine squared, that would be cotangent squared theta. And sine squared over sine squared is 1. 1 over sine is cosecant, so 1 over sine squared is cosecant squared theta. And there we go, we've established our second identity. And I can do the same thing with the last identity, the third identity, just by taking equation 1, cosine squared plus sine squared equals 1, and this time dividing everybody by cosine squared. So I have my cosine squared plus sine squared equals 1, and I'll divide everybody by cosine squared. And then this simplifies to give me cosine squared over cosine squared is 1. Sine over cosine is tangent, so sine squared over cosine squared is tangent squared. 1 over cosine is secant, so 1 over cosine squared, that is secant squared. And there we go. Those are all three of our identities now established. Okay, so when we're simplifying trigonometric expressions, there's a bunch of different things that we could do depending on what the expression looks like. So basically what we're doing is using the identities that we already know to help simplify these expressions. So some things that we might do could include rewriting things in terms of sines and cosines or using our reciprocal identities. So for something, for example, like this, where we have sine times secant times cotangent, I might decide to start off by saying, well, I know that secant is the same thing as the reciprocal of cosine, and cotangent is cosine divided by sine. And so we can see that actually a lot of things will cancel here. The cosine and the cosine would cancel, the sine and the sine would cancel. So actually we would be left with 1. So as it turns out, that expression that we have, sine theta, secant theta, cotangent theta, that's equal to 1 for any valid angle theta. So as long as those functions are defined, then we would have that it's always equal to 1. Maybe we need to use even or odd identities. Here, the reason why I'm thinking about using those is notice that we've got cosine of negative theta and sine of negative theta. So what I might do here, I might say to myself, well, I know for starters that cosine is an even function. So I know that cosine of negative theta is the same thing as cosine of theta. I also know that sine is an odd function, so sine of negative theta is negative sine of theta. And so I've got negative cos theta over negative sine theta, which is the same thing as positive cos theta over positive sine theta. And cosine over sine, that's cotangent. So the expression that we have simplifies to give us just cotangent of theta. Maybe we might need to use one of our Pythagorean identities. So this is something that you might think about doing if you see something like a sine squared or a tangent squared or a cosine squared. That might be an opportunity for you to use one of your Pythagorean identities. The one that I'm looking at here, I know in the denominator I have secant squared minus 1, and I'm thinking about that Pythagorean identity, tangent squared plus 1 is equal to secant squared. So, in other words, I could rewrite that identity where tangent squared is the same thing as secant squared minus 1. So that's my goal here. I'm going to start out by replacing that denominator, that secant squared minus 1, with something equivalent to it, tangent squared. So I'll say that we have here tangent cubed over tangent squared. And of course, that's the same thing as just tangent of x. Maybe we might need to factor and perhaps apply some other identities. I'm looking here, and if you're looking at this expression, I mean, you could think about a bunch of different things. Maybe you might decide to turn tangent squared into sine squared over cosine squared. That's a possible way to approach things. Maybe you might decide instead to replace tangent squared with secant squared minus 1 using one of those Pythagorean identities. That's another approach you might take. But I'm going to go with the more obvious thing here, which is we have cosine theta as a common factor. So I might first just say, well, why don't I factor out cosine theta out of the two terms that we have and then see what's left over. And so when I factor cosine theta out, I'm left with tangent squared theta plus 1. And here's where I'm thinking about my Pythagorean identity. I know that tangent squared plus 1 is the same thing as secant squared. And I also know that secant is the reciprocal of cosine. So secant squared is the same thing as 1 over cosine squared. So we can do a little bit of canceling, and what we would be left with would be with 1 over cosine, which is the same thing as secant theta. So that initial expression that we have simplifies really just down to secant theta. This is something that you might want to do occasionally. If you've got a two-term expression, you could create a difference of squares. And that may be potentially helpful. The reason it might be helpful is because if you're thinking back to those Pythagorean identities, a lot of those could be rewritten as a difference of squares. So for example, you know that tangent squared plus 1 is equal to secant squared, but that could be rewritten as tangent squared minus secant squared is equal to negative 1. So in other words, if you had this difference of squares, a tangent squared minus a secant squared, you could replace that with a negative 1. And you know that you would be able to make a difference of squares if I have tangent plus secant, and if I were to multiply top and bottom by the conjugate, tangent minus secant. Then we know from earlier that the denominator would be the same thing as when we have a plus b times a minus b, we're left with a squared minus b squared. And that's the idea that I'm using here. Multiplying something by its conjugate will give me first thing squared minus the second thing squared. Now, in the numerator, I'm just going to leave it for now as cosine multiplied by tangent minus secant. I'll deal with that on the next line. Okay, so we had that tangent squared minus secant squared. That was going to be equal to negative 1 using our rewritten Pythagorean identity. Again, remember that the whole reason why we were doing this was because we knew that tangent squared plus 1 was equal to secant squared, which meant that tangent squared minus secant squared would be able to be replaced with negative 1, and that's what we're going to be doing in our denominator. So the denominator is negative 1. For the numerator, I'm going to simplify my life here by first off rewriting this as cosine times tangent minus cosine times secant. And I'm going to now simplify this by rewriting tangent and secant in terms of sines and cosines. Tangent is sine over cosine. And secant is the reciprocal of cosine. And a bunch of things are going to clean up nicely for us here. I'll have that the cosine and the cosine will cancel, and the other cosine and the other cosine will cancel. So really what I'm left with here is sine x minus 1 over negative 1, which is the same thing as positive 1 minus sine x. And so there we go. I have now that my original expression could have been simplified down to give me just 1 minus sine x. Now, I do want to say that there are other things that you could do. This was one approach that I took to simplify this expression, but I do want to say that there are other ways that I might have tackled the same problem. I might have decided to take, at my first move here, to rewrite tangent and secant, perhaps in terms of sines and cosines. That might have been my first move. And then I might have decided to simplify this complex fraction by multiplying everybody top and bottom by cosine. That might have been a first move, and then I might continue on from there. So it's not that there's always only one way to proceed. Remember that any identity that you apply, if it's a valid identity, then that's a valid move to do. So that means that things like replacing tangent with sine over cosine, you can always do that. You can always replace secant with 1 over cosine. Those sorts of things are always available to us. They might not always get us to where we want, but they're always worth trying. And that, just like we had with solving exponential equations and solving logarithmic equations, how there might be more than one way to solve that problem. Same thing with simplifying trig identities. Sometimes more than one identity might apply.